Thanks, Hong, for the introduction. My name is Tianxiang. Today, I will talk about Matryoshka, our production system for realizing data center network designs, translating high-level network design intents to concrete switch configurations. The name is deliberate. So like nesting dolls, our system unwraps the network design layer by layer. The question we aim to answer is how do we convert a network design to a running network? Someone has to assign IP to interfaces, configure BGP sessions on every device, generate vendor-specific configurations, and do this for thousands of switches. At a meta scale, nearly 900 data center networks, this is not a scripting problem, it is a systems problem. The critical intermediate step, generating thousands of switch configurations from a logical design, is almost entirely absent from the literature. Academic research focuses on net topology design and post-deployment management. Industry relies on scaled scripts and many workflows. And this gap is especially occurred in the AI era where clusters are scaling faster than ever. To set the stage, let's take a quick look at Meta's data center footprint. There are over 30 Meta-owned data center regions globally. Most of them are located in North America, with a few in Europe and Asia. In each region, there are typically several data center buildings, each hosting a front-end fabric and a number of back-end AI zones. Together, they form a regional DC network, including both front-end and the back-end. This infrastructure has been evolving rapidly. In 2024, we introduced the four-plane fabric architecture. Around 2019, we moved to a fabric architecture with 16 planes, plus a disaggregated fabric aggregation layer. Then starting around 2020, AI back-end clusters emerged, introducing entirely new network designs, like non-scheduled fabrics and distributed scheduled fabrics. Each generation brought new topologies, new device roles, and new configuration requirements. Now let's walk through three challenges that make this a genuinely hard systems problem. The first is hyperscale. Horizontally, we operate nearly 900 data center networks. Vertically, AI clusters are getting bigger and bigger. Our current supercluster interconnects over 100,000 GPUs, and we have announced plans for gigawatt-level AI clusters. The sheer number of switches and the scale of the individual networks means that the computation generation must be both fast and scalable. The second challenge is the rapid evolution and growth. Over the past 6 years, we have introduced more than 16 data center designs with over 30 new device roles. Every week, we execute 800 to 2,000 config generation changes over the 900 networks. This includes both greenfield construction of new clusters and brownfield upgrades of existing networks, like a platform upgrade and link speed increase. The third challenge is heterogeneity. We deal with diverse vendors, switching operating systems and GPU platforms. The hardware landscape ranges from successive generations of NVIDIA GPUs to Meta's own MTIA accelerators, from external vendor switches to our in-house FBOSS platform. The heterogeneity is only growing. On the AI side alone, we have over 100 AI zone versions, each being a unique network configuration. So what is a Matryoshka? Matryoshka is an intent-based, model-driven system that compiles high-level network design intents to concrete and correct switch configurations. The name captures two key ideas. First, like a nesting dolls, modular topologies nest within larger topologies. A collapsed block can be replicated and composed to build networks at any scale. Second, configurations are progressively conceptualized layer by layer, from abstract intent down to bundle-specific configs. Matryoshka has been in production for over 6 years. Today, 100% of Meta DCN infrastructure is supported with Matryoshka. Nearly 900 networks across 18 data center designs, including our 100K GPU AI supercluster that powers the large language model training. There are 5 principles that guide our design and implementation over the 6 years. First, we build a complex topology by composing simple building blocks. In particular, any data center topology can be represented by combining just the 4 grapholate primitives: complete bipartite, ring, mesh, and circulant bipartite. Second, we model the entire end-to-end design realization workflow, including intent modeling, topology generation, IP addressing, routing, and native switch config generation. Third, we use Swift-based declarative models for network design intents that are capable of defining a network in any operational state. Fourth, every time we generate config, we recompile from scratch. Brownfield updates are identical to greenfield. This avoids state drift bugs and simplifies troubleshooting. Last, we utilize the generic switch configuration interface, which abstracts away vendor differences. So the same logical config can target any vendor platform. Matryoshka has 3 layers, like a nesting dolls. The innermost layer is intent modeling. A thrift network-based network spec declares what we want: topology type, IP addressing scheme, routing policies, and hardware platforms. Those specs are version controlled and validated on every stage. The middle layer is intent realization, a coarse to fine pipeline. It starts with switch entities, including host names and hardware platforms. Then topology. We decompose the network into grapholate primitives and compose them. Then IP addressing, hierarchical allocation from top-level subnets down to port-level assignments. Last, routing, including BGP sessions, peer groups, and policies. The outermost layer is a switch configuration. Our generic switch configuration abstraction captures the full switch config in vendor-independent format. It is then translated to the vendor-specific configurations by dedicated vendor converters. Matryoshka operates within a broader ecosystem. Network specs are the input, version controlled, and validated on every change. Akpinar is our network modeling database, storing the logical model of the entire network. Generic switch configs are the output, stored in the repository, and deployed to switches via the configuration validation service. A key property is that Matryoshka is stateless. It recompiles everything from scratch. But for database updates, it computes incremental differences between the current and the desired states, reducing transaction time by up to 99%. Validation happens at every stage, from spec validation at input to GSC validation at output. Now here is the ultimate stress test, Meta 100K GPU AI supercluster. This is the infrastructure that powered our latest large language model training. The cluster spans 6 buildings. 3 were repurposed from existing traditional fabric networks through brownfield migration. We expanded 4 rocky clusters per building to 8 AI zones. 2 additional buildings were constructed from scratch for the AI backend. There's one building dedicated to storage. The front ends and the back ends of the 6 buildings are interconnected via their respective front-end aggregation layers. Matryoshka handled both the brownfield migration and the greenfield construction via simple changes to the network specifications. Now let's look at the performance results across 4 dimensions. First is correctness. 95.4% of Matryoshka-generated configs pass switch config validations on the first attempt. Our daily end-to-end build have a 96.4% success rate. More importantly, failures can be caught before reaching production. The configuration move service blocks any invalid config from being deployed. Second is efficiency. Originally, Akpinar database transactions of Matryoshka were extremely slow because when updating a network database, we had to delete and recreate the whole network. To address the performance issue, we invented a generic database updating algorithm which can construct database transactions based on differences between current and target states. This algorithm supports any type of network migration operations and reduces transaction time by 70 to 99% on average. Scalability. Processing time of Matryoshka grows linearly with the network size, measured by switch count. It is primarily because a combination of factors. One is switch config generation time dominates the processing time. And the second, Matryoshka is developed in Python, which lacks native support for parallelism. Last is extensibility. Matryoshka adopts object-oriented programming principle from day one. Its main system architecture is fairly stable. It has been extended to more than 16 new DC design types over the last 6 years without significant architectural revisions. Let me share some lessons from the 6 years of production operation. First, large blast radius. A single bug in Matryoshka can misconfigure thousands of switches. In 2020, a bug during brownfield migration accidentally deleted all the IPv6 prefixes across the entire DC region. This prompted a major investment in an abstract invariant validation and end-to-end regression testing across all 18 DC tabs for every code change. Second, system complexity and maintainability. We learned in the hard way that the migration-specific solutions are easy to adopt at the beginning, but never scale. This motivated us to adopt the deterministic and stateless design principle, which has proven effective in supporting various migration operations via a generic code path. Third, validation-aware config deployment. Software systems always have bugs, no matter how well tested and maintained. Therefore, it is more efficient to explicitly qualify a switch configuration in terms of desired configuration validations before deploying it to production. This approach also facilitates troubleshooting. Fourth, evolving to meet new challenges. As we keep inventing new DC designs, configuration for new product introduction has become a constant demand. We are revolutionizing Matryoshka architecture so as to reduce the NPI cycle from 1 quarter to 1 month. By doing so, we hope to keep up with the cadence of meta data center network evolution. We conclude our presentation by sharing 3 takeaways. First, DCN configuration realization is a first-class systems problem, not a scripting afterthought. At hyperscale, we need a principled automated solution. Second, modular stateless compilation scales. Our design observed 6 years of growth, including the AI revolution, without architectural changes. Third, the AI era makes this approach essential. The heterogeneity, the pace of change, and the sheer scale of AI clusters are simply too great for ad hoc methods. We hope this work inspired continued research toward intelligent, scalable network design systems. I'm happy to answer questions.